One of the most incredible accomplishments in the modern era of astronomy is the rise of gravitational waves. That in 2015, the LIGO Observatory detected two black holes crashing into each other. And then further versions of the LIGO, more upgrades, have allowed them to discover many more of these objects. At its most recent run, it was finding one object a week or so. But there's a limit to what LIGO can detect. It can detect stellar mass black holes, but it can't detect the merging of supermassive black holes, potentially intermediate mass black holes. We need a different kind of observatory to be able to do that. A space observatory. And the European Space Agency has known about this for a very long time, and they're working on their LISA mission, the Laser Interferometer Space Antenna. And this is a trio of satellites that will fly in perfect formation, sending lasers back and forth to one another across tens of thousands of kilometers. And then as the gravitational wave of a supermassive black hole collision washes past them, it will change the length of the legs on this triangle, and they will be able to detect it. And that's just one example of the kinds of things they'll be able to find a lot of other stuff. And we're not going to see this mission fly probably until the 2035-ish range. But ESA is working very deliberately to make this happen, and they have already flown the LISA Pathfinder, which was essentially one of these satellites with a bunch of prototype technologies inside of it to demonstrate that this technology is feasibly going to work. The science results are in, we know that it's going to work, and now people are working on the next generation. And so my guest today is Dr. Stefano Vitale. He is the principal investigator for the LISA Pathfinder mission and has been helping to design the LISA mission for the European Space Agency. In our interview, he explains what happened with the LISA Pathfinder mission, what they learned, what parts actually came out better than they were expecting, and how this prepares them for the actual final construction of the LISA mission in 2035. So if you want to hear how it all went directly from the principal investigator, the designer, the architect, enjoy my conversation with Dr. Stefano Vitale. Just a warning, when we recorded this, had the wrong microphone, and so we've had to clean up the audio, and you have no idea how much work Anton went into to make this better. So I know it's not perfect audio, but it's so much better than what it was. But it was such a treasure to talk to Dr. Vitale, so we knew you wanted this interview.
Stefano, you've been thinking about gravitational waves before they were detected, for decades.
Oh, yeah.
What was it like to, you think, sort of imagine gravitational waves, and did you think that you would find them in your lifetime?
Good question. Yes, I was convinced that we would have gotten them within our lifetime. I started with the first generation of ground-based detector, which are this resonant bar. You may remember, I did one cryogenic one in northern Italy. It was clear that those probably would never detect anything, but the interferometer were more promising, still very uncertain. But then when I met LISA with guaranteed sources, if you believe general relativity, then I said, I want to do LISA, right? Because LISA, the binary in our galaxy, we can calculate the signal. So unless general relativity is wrong, LISA would have detected a signal, right? In the time of uncertainty, LISA was a beacon.
Right. I like that idea that when you met LISA, was it that when you met the proposal?
I entered the European Space Agency system because I was asked to consult about mechanical system for another mission. And I knew that Karsten Dansman and other people had proposed this space-based interferometer. This was in 94. I say, yeah, that's what I want to do. So, and I decided to join. So I joined in 95. While the project is from 93, I joined in 95. Long ago.
And people think that waiting for the James Webb Space Telescope to be, that's about the same time that James Webb was conceptualized. And we only just saw the launch. It has been all 30 years from that. And with LISA, we're still 10 years away. So it's a 40-year journey to go from here's the idea of a space-based interferometer to
It's more complex than
actual
that.
launch.
The first paper that describes LISA is a paper from Jim Fowler and Pete Bender, and is in '84. So it will be 50 years from the first idea. But in the meanwhile, we did a preparatory mission, right? We were not just studying; we flew LISA Pathfinder, which made a difference because we had a problem of trust. Does this thing really work? A pretty legitimate question.
And that's a fascinating way to approach this idea. And I don't think I've ever seen this done in the same way, that they launched a complete mission. Its only job was to test a whole bunch of these key technologies in space just to make sure that they're actually going to work. So what were you worried about that you didn't think might work as they were developing LISA Pathfinder?
Yeah, you need what I call assisted luck in space mission.
Yeah.
So, and what can go wrong is what you don't see coming, right? So the question is, being many people, the best brain around, and keep thinking. And we thought everything. And apparently, LISA Pathfinder demonstrated that the procedure works, right? So apparently, we had worked at least 95% of it. There are a few things in the data, despite the result were amazing. But still, we are, digging in the data to understand the most minute details. But it was a huge effort of physicists, engineers to predict and calculate and think and put margin and not to run any risk. Obviously, if LISA Pathfinder would have failed, you could have kissed goodbye a space-based gravitational wave detector for decades or centuries, right? The people would say, "Oh, this doesn't work. That's too difficult. You cannot do a test on ground, so it's too difficult," and forget it. But we were lucky, or I would say my colleagues were very good.
Right. Yeah. So I guess what were you looking to see with LISA Pathfinder? Like when you launched LISA Pathfinder, there were a bunch of paths that needed to be passed to say, okay, a space-based interferometer is going to work.
Yeah, well, the key question is the following: to do a gravitational wave detector, you need bodies in free fall, no forces that disturb them, so they move only under the effect of gravity, and you need to measure the distance between the two, right? So the science is twofold: perfect free fall and measurement of distance. The people were convinced that the measurement of distance you could test on ground almost entirely, and it's a physical. The free fall we needed is we have this word femto g, a millionth of a billionth of the Earth gravity. So anything in excess of a millionth of a billionth of the Earth gravity would compete with LISA science. 10 times, LISA is not worth flying. 100 times, you wouldn't see anything. No, 10 times, maybe still it would be worth flying, but much poorer instrument, right? So, what can you test on that? Well, on ground, at the end, we invented some method to retire some risk and test for some effect, but uh, basically 1,000 times worse, and no way to test this end to end. And so the goal was so fantastic having this detector that very boldly the European Space Agency was very courageous to say, okay, we give you a chunk of money and demonstrate that you can do free fall at this incredible level. Right? When we give outreach talk, we say this is the same as the weight of a virus in your hand. Right? If you put a virus in your hand, the weight is a femto g. Right? So
So what was the apparatus? What did it look like? Like if you could sort of open up LISA and look at the machine that's testing the gravity.
the apparatus is A LISA arm, a LISA arm is 2 test masses and an interferometer, and it's 2 million kilometers. We took the 2 million kilometers and squeezed in a half a meter inside the spacecraft, because if these test masses move without any forces, will not accelerate one relative to the other, you don't need a million kilometers because the disturbances are local. And so that was our complement: two gold platinum, very clean, very perfect test masses, and an interferometer measuring picometers, proper distance at picometer. And if you measure at picometer, and they are floating in the spacecraft, nothing touch it. There is no wire. These are, and the spacecraft moves not to touch them, right? So it's a perfect free fall. The spacecraft is a shield. You measure where the test mass is and move the spacecraft to avoid collision, right? That's the concept of not touching anything, because that's what you do. You put these test masses in free flight that in space you can do, right? You have seen the astronauts, putting pens and pencils in free flight. You put this pencil in free flight, and you really don't touch them, right? And then with the interferometer measure the distance and look for jitter. More jitter, bad. No jitter, good, right? And so the more than jitter, you measure acceleration, and we had requirement to try to get at the level LISA need, maybe 10 times worse. People would have been more than happy, thinking, okay, we learn a lot and then we will design LISA, but we did better than LISA needs, slightly better than LISA needs. So we had fine colors and liters of champagne.
So if I understand this correctly, you have these like two floating masses of this really pristine mix of metals inside this spacecraft that, as you say, acts like the shield. And then you're bouncing a laser back and forth between the masses to make sure that the distance between them remains exactly the same and there's no jitter, as you say. And then if the
At the
spacecraft
frequency,
detects,
yeah, there are more details, but
right,
the basic is that.
and if the spacecraft detects that maybe one of the masses is about to bonk into the wall of the test chamber, it shifts itself a tiny little bit to keep everything nice and balanced, so that you can have this pure test of gravity inside the apparatus.
In reality, let me give you
Yeah.
a little detail because somebody could be confused. In LISA, the spacecraft follow one test mass perfectly, right? So if the test mass moves, the spacecraft moves to avoid collision. Avoid collision means that it's centered within a fraction of a nanometer. That's the precision. Anyway, in LISA Pathfinder, because you have two, you cannot follow both. So the spacecraft follows one, and the other one, unfortunately, we were forced to give a little force electrically, which was the limit of the test. And so that's the reason why they said, okay, you cannot do LISA, but try to approach LISA. But in reality, we did perfectly. And the electric force we had to apply was much less than we were prepared to. We knew that it would have been less, but we were prepared to the worst. And so because it was much less, the performance was the same as in LISA. Otherwise, we would have paid the price, because these electrical force are a bit noisy, right? You generate the force with an electrical generator. Those generators are noisy, and the force is noisy. But fortunately, the force was so low, so faint, that its noise is still limited the performance, but at the level that was better than LISA, slightly better
So
than
so
LISA.
then so you've got this exquisite test of gravity. I mean, did the physicists learn anything about gravity? I mean, I guess Einstein was right again? Is that what you learned?
No, the physicists tried anything. They also tried to send us to a magic point between the Earth and the Moon to demonstrate some fancy theory of gravity. But honestly, my colleague and I resisted We said on our dead body, because we want to do LISA, because that's where the enormous knowledge jump will happen. And so you may find this very fancy and ask for measuring this and that. While you're there, why you don't try to measure that? We said no, we have a clear goal, and now we have been rewarded with the approval of LISA, right? The answer is no, we didn't do anything. We also published the measurement of big G, but it's very poor. I wasn't very enthusiastic of that, that little piece of work.
And so the European Space Agency announced that they're going ahead with the full implementation of the LISA. And this now has the construction of 3 satellites that are going to be flying together and attempt to test gravitational waves. So what, when we're all very familiar with the kinds of gravitational waves that have been discovered with LIGO, with VIRGO, KAGRA, that you've got these, black holes of varying masses crashing into each other, neutron stars colliding with one another. What mass regime will LISA, the full LISA in space, try to look for?
Yeah, the 100 million question. The reason
100 million
why
solar mass question.
the million solar mass question, yes, that's more expensive. The reason why we do LISA is that you cannot access low frequency on ground. Our colleague on ground are working above 10 hertz. Hope with the next generation may be to reach a few hertz. Below that, the motion of the atmosphere and the Earth crust generate a gravitational field that covers any astrophysical signal. So if you want to go to lower frequency, you have to go to space. At least nobody got any cheaper idea than going to space. That's the reason for LISA. So LISA will be in the microhertz. Now, remember, most of the sources of gravitational wave are 2 bodies spinning one around the other, right? And the frequency of the wave is twice the frequency of the spinning. And the frequency of the spinning, well, that's you have to calculate, but believe me, right? So more or less, if it rotates at 1 hertz, you get a wave at 2 hertz, something like that. So to go to microhertz, you have to have things that rotate very slowly. Or if you go to microhertz, you access things that rotate very slowly. Now, remember, the rotation rate is, I don't know, from your high school, the Kepler law, right? The rotation rate depends on the mass and the distance. And if you calculate, the larger the mass, the slower the rotation. And the larger the distance, the slower the rotation. So if you want to test bodies that are big, or you want to test bodies that are well separated, you have to go to low frequency. That's the reason for LISA. And so it's basically 2 branches. One is supermassive body. Our colleague, the fantastic science that our colleagues are doing on ground is they call stellar objects. It's not stellar. They go up to 100 times the mass of the sun, maybe even 1,000, right? So it's a big stellar on steroids, right? Here we are talking million solar masses, 100,000 to 10 million. So you're talking the big black holes that are in the center of the galaxies. And the astronomy of those is a totally different. Now we know that all galaxies have a black hole in the center. It's like the yolk in a egg, right? So when these 2 massive black holes start, encounter and start rotating, they carry the galaxies with them. And so you have this, I don't know if you've ever seen in the Hubble Space Telescope picture, this interacting galaxies that are locked in the gravitational field, one or the other. In reality, in the middle, in the center of those galaxies, there are 2 black holes spinning, and they will spin, enter in the LISA band. Some will be followed by many, many weeks or months or years, and then there will be the final spin down with all the galaxies around. or these huge bodies will capture a small one, and the small one will do a sort of Gottdammerdung before plunging into the event horizon. So fantastic, general relativity laboratory. Don't ask me the details, please, to not to embarrass me. But I mean, that's where the large physics. The other side is the binary in the galaxies. Astronomy, as was known, when you see a source, the source is there and start and it keeps shining in the sky. That you cannot do with the ground-based one, right? These are all transitory. So you do the science of the binary in the galaxies. LISA should be able to discriminate 10,000 of these galactic binaries. And so the appetites of 10,000 distinct, 10,000 peaks, the frequency resolution is so good because it goes for years, no? That you see these little lines that are different binary system in the galaxy. And so you do the science of the binary system, and many of those are invisible electromagnetic. Some are visible, some has no electromagnetic counterpart. So this is a different astronomy. And also the supermassive black hole, because the intensity of the signal grows with the mass, the supermassive black hole are basically visible everywhere in the universe.
Wow.
Basically some of those, the signal to noise ratio is so high that they are visible at redshift of 20. I know that I can use redshift of 20 or more. So we don't know if they exist, though James Webb and others are discovering continuously candidate black holes where we were not expecting the black holes to be. So
So you're going to be able to see those supermassive black holes merging pretty much throughout the universe out to just the 100 million, 150 million years after the Big Bang. And that will help us answer, what kinds of fundamental questions about the universe will that help us answer?
I know, because I listen to the talk of my theoretical colleagues. I know that they basically want to do how will you call it, stratigraphy of how the galaxies that we see nearby us formed by merging, and how those original black hole formed. This is one of the big mystery. LIGO and VIRGO discovered a lot of black holes. We were not expecting those black holes. How were they formed in first place? And how this gigantic black hole in the center of the galaxies were formed in first place. And so now you have to think that any of this binary sooner or later will enter in the LISA band. And so LISA could do a stratigraphy of doing the farthest one, the closest one. And so you see the history of formation of the big nearby one by mergers of the old one. So these are the kind of question. Then there are also, for instance, this signal from the capture of a small object from a black hole, like a small black hole that falls in one of the supermassive black hole. The people calculate that it will emit detectable waves for 100,000 orbits, giving a map of the event horizon. And there you can test, is general relativity good to all digits? I mean, the signal to noise ratio, if you're lucky, the signal to noise ratio could be so high that you could start, digging into deviation from general relativity. That's why the people say it's a fundamental physics laboratory.
Like with a lot of astronomy, with each generation of telescope, what was blurry before becomes a stronger signal, and you have less noise and you have more data. But with this, it's very strange. It sounds like once you're able to perceive the long wavelength, then suddenly a whole new part of the universe opens up to you with signals all the way out to pretty much the beginning of the universe. And that feels very different than what I think about, like a new telescope getting more powerful.
It is different. Yeah, it is different. That's the short answer. Is it is different. It's more, for years we have advertised that this is more sound than light, right? Is this and it's like listening with an ear, listening the entire environment. You have a pretty good discrimination. My colleague Bernard Schutz, one of the famous astrophysicists, showed in his seminar a picture of a jungle with the audio cut. So you see the forest, a waterfall. It's beautiful, but very, And then you turn on the sound. And when you turn on the sound, you hear the waterfall, and there is full of animals, scratching, crying, making all sorts of noise. And you can also locate them. You can associate even a picture if you're lucky, and this is the electromagnetic counterpart. So the analogy with sound that could seem a cheap outreach trick, it's more deep than you think, right? It's more like, this is a different probe. It's not photons, it's a different probe, and it looks more like sound, where we have these big ears to locate the sources. I mean, remember in Second World War, the Brits located the German aircraft also with sound before the radar was good enough, right? So some similarity there,
Yeah.
though this is.
And so I want to follow that other branch now. So you talked about this idea of essentially wider binary stellar objects that are orbiting one another within the Milky Way. What could we learn from them?
Okay, I'm the wrong person, right? I'm not an
Yeah, I know.
astronomer. As I told you,
You're the
I'm a
mechanic.
plumber. I'm a plumber. I have a wrench. My tool is a wrench. Um, uh, I did actually. Really, you should ask the expert. But it's a survey science on binary. I can tell you a few things that I learned. For instance, the sensitivity of LISA is enough to detect a planet around this binary. The perturbation of a planet around one of this binary will be visible in the signal. These are the
You could
kind of
detect a
things.
planet orbiting two
Uh,
black holes.
no, two white dwarfs, because those
Okay, sure.
those,
Yeah.
those
No,
are
that makes
those are compact
that's fine.
binaries. Must be compact, not big
Yeah.
stars. Must be compact, otherwise it's not a separated, right? But it doesn't need to be black holes. Actually, the largest fraction is not expected to be black hole, but to be this active X-ray things, the white dwarfs, and so on. And another interesting branch. As soon as my LIGO colleague detected the first black hole, one of the LISA people, Alberto Cesana, calculated that if LISA had been on orbit, that black hole would have been detected, separated 10 years before, followed for years, no, 10 years, maybe 1 year, I don't remember, a few years, followed for years, then for the last, and then 1 week before would have disappeared from the LISA band. The LISA people would have called the LIGO people and say, hey, there is a black hole that will appear in band in a week from now at this time, that day. And this is not just a curiosity. It seems that you do a fantastic science following the signal throughout all the evolution. So this is called multiband gravitational wave astronomy, and so you realize what you can do with that. So, and this is what we are able to think. Remember that the LIGO and VIRGO people were aiming at neutron stars. There were no black hole out there that they could detect, right? They went on the air and detected just black holes that nobody had thought of through. So this is what we think of, but then what we'll see.
But that's so tricky. Like always finding, say, supernovae. It's about seeing them after. Like, oh, you noticed this bright star that appeared in this galaxy. But to be watching, say, a neutron star, two neutron stars orbiting one another for 10 years, and then they disappear off of the LISA spectrum, and then you give a date and you say, hey, anyone with a telescope, look at this galaxy at this day, at this time, and you're going to see a kilonova. I mean, obviously, then the opportunity is to see the precursor, to point James Webb at the two neutron stars that are, or maybe Chandra, at the two neutron stars that are orbiting one another, and watch them
that's a good point.
for
I
every
must
part
say,
of this collision.
I must say the not all will be visible, right? It's only a fraction because they are pretty faint where they are in the LISA band. So I don't know about two neutron star. I would be surprised if not, but certainly the black holes binary, that's where the calculation was done. For those,
Yeah,
the calculation showed that they would have been visible. So I don't know the
Yeah,
details, but that's the more or less the science.
Yeah, but I mean, astronomers would be so happy. It could, again, like, this is their great challenge, is to find the thing before it explodes, because they only find it after. There's only a couple of chances where they actually saw something before it happened. So where are we at now? So we've got, the European Space Agency has given LISA approval. So what happens next?
Okay, so what ESA is doing now is preparing an invitation to tender for an industrial contractor. This is a competitive tender. Even the study phase has been done in competition between two contractors. That's used to avoid, being in the hand of one provider. And once the expectation is that the contract should be delivered at the beginning of next year. That's the time that it takes, right? And then no, it's a lot of also just bureaucracy and negotiation that is necessary. These are, I don't know if you heard the amount of money he's setting aside, which is 1.75 billion. So it's a considerable amount of money, and so there are industrial regulation that has to be obeyed and so on. So this is a technical time. You have to prepare a very accurate description of what you want from the contractor to avoid surprises. In the meanwhile, many of the most sophisticated part of LISA are coming from institute/industry of the ESA member state and from NASA. For instance, Italy delivered the gravity reference sensor, the test mass system, right? Germany as the lead in a consortium with the UK and the Netherlands and so on to deliver the interferometry, the key part of the interferometry. NASA delivers the telescope, which is used for the communication between the spacecraft to send the laser beam from one spacecraft to the other, and the laser. All the lasers on board are provided by NASA, and one of the system of the gravity reference sensor, which is the charge management. So those items are under development. You may call this separate projects. ESA is overviewing all that, but obviously the Italian contribution is delivered by Italian Space Agency, et cetera, under the responsibility by the scientists and industry. And so you will go through now the timing. I don't have a Gantt chart of the project, but basically, you go through preliminary design review, critical design review, and a phase where this is the phase where you do models of everything, right? Engineering model, qualification model. You learn how to build the final things. And then it starts the most challenging part of LISA, because LISA is not only a new thing in gravitational waves, but it's also a new thing in space science, because there aren't many, to use an understatement, there aren't many missions that has flown 3 satellites that needs to be in locked contact each one being in locked contact with the other two in order that the things leaves, right? Many constellation of satellites, you lose a satellite, okay, you lost a satellite, but the other continue, right? LISA, no. If you lose a satellite, the mission is over, right?
Mhm.
And so you have to build these three very sophisticated things. That means that you have to try to parallelize a lot of activity, but you need pretty sophisticated manpower, human power to do that. So you cannot just hire generic people. So it's an incredible industrial challenge, And ESA has been very brave to take it. I think they have the capabilities to do it, but certainly it's a challenge and requires a lot of good management. But I'm pretty optimistic. But it will not be easy. It's not going to be easy.
I mean, thanks to LISA Pathfinder, you were able to remove some of the unknowns. What are the parts of the project that you think are going to be the most difficult from an engineering standpoint to make it work?
I mean, the technology, strictly speaking, is in pretty good shape. The challenges are that there is not much you can test before you fly. That's one challenge, right? So it's not so much that the laser will be difficult. Actually, the laser is going very well. Or the telescope is going to be difficult. It's going well. The optical bench, it's a very sophisticated piece of equipment which is delivered by UK. We flew one on LISA Pathfinder, smaller, simpler. This one must be, we need 7 of now, 6 plus 1 spare, right? 2 per spacecraft. This is an incredible industrial challenge. It's all about producing it, right? It's not that we don't know how to do it. We know how to do it pretty well. Well, a few details. Maybe we still have to refine something, but those are details, some mechanism, something like that. But the key part we know how to do. They have been developed over the year. While we were flying LISA Pathfinder, the people were not just waiting, right? They were developing those technologies, so they are pretty mature. Uh, but the question is implementing them in six copies in three spacecraft on time, on budget, and without disasters, because that's you need to build redundancy and resilience in your organization. To me, that's the most difficult part of the implementation.
So let's fast forward 10 years ish, and now you're ready for launch. And you're on, I'm assuming, some Ariane rocket, and the 3 spacecraft are carried out to their orbit. What happened next?
It happens. Each spacecraft has its own propulsion module because you launch them together, but then they have to split, right? Because they have to go in 3 different orbit. This magic orbit where they form a triangle with no need of maneuver, right? And to do that, you need a propulsion module. The entire thing requires a year and a half of navigation from launch to acquisition of the constellation with all the laser pointing in the right direction. It takes about a year and a half. During the final part of this year and a half, there will be a lot of commissioning to try to save time, right, for scientific operation. And then we or they, because my life expectancy has to be folded in here. They have to acquire they have to do also a very new operation because nobody has tried to lock. So the spacecraft has to find each other and then stay locked on the laser, right? So the turning is dictated by the fact that the laser must be locked, that the laser that is sent here is received here and vice versa. And so this is a sophisticated procedure. We think we know how to do it. We have also 2 or 3 fallbacks. I mean, the things is under control. It requires a lot of dedicated instrumentation to do that. And then once you have acquired, basically as soon as you acquire, you start to get data. Now, what kind of data? I mean, LISA Pathfinder on first day of operation worked. I'm sure LISA will do the same, but let's cross finger. It's difficult, huh? It's a difficult mission. On the other hand, if it weren't technologically difficult, you wouldn't do this mission. Let's be honest. One purpose is to serve science. The other one is to advance space technology, right? And so it cannot be dull, right?
And so, I mean, when we think about telescopes, we think about that commissioning phase, and then there's this first light. But I guess it's like first sound. You're gonna
First
hear for
sound,
the first
yeah.
sound. Yeah,
First sound.
yeah,
That's
interesting.
correct.
Yeah.
Yeah.
And how long is it expected that LISA will be able to operate for?
Okay. Here I may not know some of the details because I've been not following the industrial development. Other people were doing that, but I think the baseline now is I think 6 years of operation from the beginning. So it includes commissioning, but the system is designed to last 10 years.
Hmm.
And
And
usually
is
you get
propellant?
Yeah, propellant is not a problem. As far as I know at this very moment, the problem is the stability of the orbit. So without a maneuver, after 10 years, the constellation drifts so far away from the Earth that communication is not possible at a
Oh,
sufficient level anymore.
oh, that's interesting. Yeah, yeah. Oh, a lot of people don't realize that in many cases the problem is not about keeping the spacecraft going. It's about being able to communicate the data back home. That the farther you go from Earth, the bigger a transmission system that you actually require to send a signal, and especially if there's going to be a lot of data in it.
Yeah, and that LISA is a compromise. You would like the constellation to fly close to the Earth, but the Earth is noisy. So you make a compromise not too close to the Earth, not too far away for communication. And in reality, because this orbit drifts away, you start close and end far away. And this chunk of years is about 10 years, right?
Right, right. But imagine maybe somebody launches a relay satellite at some point. There are solutions. I'm sure if it's just doing wonderful, I'm sure people will think of clever ideas to keep it going.
To keep going, LISA, well, maybe.
Yeah,
Yeah,
yeah.
yeah.
I don't know. Who knows? Who knows?
Who
Um,
knows? Yeah.
uh,
I'm
so
sure that in 10 years we'll collect so many data that maybe the people say, "Yeah,
right,
let's kill it. There's too many
that's
data."
enough. We don't need any more. Yeah, we've got enough. Uh, well, no, I mean, I think what happens next is the bigger version of LISA. So there's
Yeah.
another plan, the Big Bang Observer.
Well,
Where's that at?
no, the Big Bang people are not really thinking anymore. However, ESA has conducted a study to get ideas for the new phase of the science program around 2050. Also, NASA is interested, and so the community has collected this, has taken this challenge, and there is an ongoing community study, not funded by anybody, to see because ESA has put a gravitational wave mission among the possible large mission of the next cycle in around 2050 or so. And so the people are studying what to do. I must say that it seems that the most popular is a LISA at a higher frequency, filling the gap between the ground-based detector and LISA. That would be a smaller LISA, not a bigger LISA, but tuned to a different frequency. However, there have been proposals to do a much wider LISA, not big, BBO is going to be out of the reach even of the most powerful international collaboration because you have to fly as a minimum 2 LISAs, right? As a minimum. And let's see how LISA
I
goes.
think it was 12.
Huh?
Yeah.
Yeah,
I think it was 12. It was 12 spacecraft.
Yeah, but the LISA spacecraft is a big spacecraft, and doing 12 LISA spacecraft now looks like a dream very far in the
Right.
future. Obviously, once LISA gets the launch pad and we'll learn how to do and it looks that it works, then we can discuss again, right? But for now, it looks more realistic reflying a one LISA with improvement and going to do a slightly different science. But we'll see.
But
The studies are ongoing.
right. But if we could, I mean, I guess like those primordial gravitational waves from the Big Bang are out there. And someone has calculated their wavelength. And if someone gives you the wavelength and says, could you make a machine to find it? You must have, like, what would it look like? What would the spacecraft that would find those primordial gravitational waves, what would
That's
it be,
LISA.
do you think?
That's LISA.
You think LISA can find the primordial gravitational waves
So
from the
the
Big Bang? Or is
difficulty with LISA is that you can detect stochastic background, a background of primordial gravitational waves only if exceed the noise. And our knowledge of the noise is in that reckoning. It's not something that you can test locally. So the people are thinking what can be seen based on the peculiarity of the background you want to detect. If our Chinese colleague that are pursuing two independent studies to do a sort of LISA, they get their act together and are able to fly another LISA in the same time frame, then you do cross correlation between the two instruments as you do on ground with the LIGO and VIRGO and so on. And then you could do, then you do the cross correlation detection, which is, and then the sensitivity of LISA. Some of the model predict that LISA should see some of those primordial background. Actually, the conflict there will be between the primordial background and the background and the foreground of binaries in the galaxies that you cannot distinguish one from the other and makes this humming in the back, right? So in order to detect that, if you solve the problem of the knowledge of the noise one way or the other, then the competition is there. How well we know those background to detect the primordial background. If the primordial background is that of the standard inflation scenario, then LISA is not sensitive enough. But it will be hard to have any instrument sensitive enough. Even the microwave background would not detect those things if it is a standard. So, but in other scenario, and so the question is a very important question. LISA has the sensitivity to detect that, may not have the accuracy, right? Because you have to detect against other noise. And the people are working hard to see if we can model things well enough that we can at least detect above an interesting threshold, right?
right. It's interesting. It's like there's so much background noise. What you call the humming, the buzzing of binary objects across the entire universe that obscure your view to
Yeah, it's
the
mostly
Big
the
Bang.
galaxy. It's mostly the galaxy.
Yeah. But we have that in electromagnetic, like in the electromagnetic side as well. You have the cosmic microwave background radiation that obscures your view to the earlier universe. And it could be that there is a different version of that in gravitational waves that obscures your view to the early universe. Just like there's
Yeah,
no,
it might be. It
can't
might
get a
be.
break.
Yeah,
Maybe
I must say for the local humming due to the binary in the galaxy, that's one of the reasons why people want to go in the decihertz band between LISA, because there is a hole. There is no signal from the galaxy at 0.1 hertz. And so the people hope that that's a window to investigate backgrounds, right?
Yeah.
That's one
Yeah.
other reason.
So what does your day look like right now? What do you like? What tasks are you working on right now as this whole project moves forward?
Me?
Yeah.
I am a retired professor, so I'm enjoying life, but then uh, so
So that's what you think anymore?
no, I'm working to LISA, but I'm doing technical work. I think the time of leading teams and jumping on an airplane and down from an airplane is in the past. Luckily, so
Yeah.
so I'm available for anything, and I mean I'm doing work, but it's supporting all the
Yeah.
teams with achieving this, right? I think that's the role of senior people, right?
If
Experience
somebody has a
and
really
wisdom.
complicated problem, they should come to you.
For instance, if I can, if I'm still alive,
Yeah.
or
Yeah.
if my brain is still alive, I could be alive, but the brain gone. We'll see.
Yeah. Well, Stefano, it's been a pleasure to talk to you. Congratulations on this long career through Gravitational Observatory,
Thank you.
being the best plumber out there. And congratulations on everything with LISA. And it would be so great for us to see those first gravitational wave detections in those longer wavelength in now about a decade, which feels like forever, but is just around the corner when you think about the whole thing. Thank you so much.
Thank you.
I hope you enjoyed this conversation with Dr. Stefano Vitale. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradron, Chuck Hawkins, Commander Baylock, Cy Nelson, Dark Finga, David Gilton, and David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Switz, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Buck, Rinkaidu, Richard Williams, Sean Sargent, Stephen Fallon Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zelda War Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So this was the lost episode. We recorded this episode many months ago, and the audio was so bad. And we had to sort of figure out what we were going to do to fix my audio. I was essentially recording from the camera, and that made for, it was like a, recording with a potato. And so Anton, to his credit, has done an amazing job of cleaning up the audio to the point that you don't suffer, your ears don't bleed as you actually listen to this episode. And the reason we went to all of this work is because the conversation with Dr. Vitale was so amazing. He is the heart and soul of the LISA mission and has been here helping to design what is going to be one of the most sensitive instruments ever developed. The sort of the ambition of launching these satellites and putting them in formation is just stunning. And yet the kinds of discoveries that it's going to give us will be groundbreaking. And we will know that there are supermassive black holes merging around us. It'll be just incredible. And yet it feels like it's taken so long. I've been reporting on the potential for the LISA mission almost for my entire career. It feels like I reported on the Pathfinder mission. Now we're still 10 years away from LISA being able to launch. And yet when it does, it'll change everything. All right. I hope you enjoyed the interview. We'll see you next time.